Thank you, Rasmus, for a fantastic introduction. Excited to be here. And I will share a story where we provided mechanisms that explain how AI solutions work. So you have already heard many of the fantastic ideas and solutions provided by the AI systems or different mechanisms. For example, as you heard, it has the possibility to read the data from different type of functions, from different type of processes, and automatically control it. Another, of course, capability is condition monitoring and maintenance. So learning from the past failures, sensing data regarding either the pressure, electricity, or some other mechanisms, and say, in 2 weeks, or maybe in 3 weeks, there will be a problem. But you don't have to care about it right now. Wait a little bit. I will give you a prediction of when the problem might happen, and perhaps even a plan and order the spare parts. Another capability is that whenever there are anomalies in their various type of processes, for example, the flotation process, it can read how some of the users, the operators, manipulate the process. So avoid and stabilize it. And through interactions, so which variable that is being actually controlled, to which degree, what is the new set point, or maybe even tracking what they look at, the information on the screen, the AI, the system can take that information through some type of knowledge management and processing, take it back into the model, and perform or avoid the anomaly next time. So far, so good. It sounds great. AI is good, but it's not perfect. It has some limitations. As you see, it has syndromes, some challenges. And some of the challenges that you already heard about, they have to do about trust, which is a complicated topic. Does it always make the decisions in the right way? Do we understand what considerations it does? For us people, we ask our colleagues, or we ask our partners, which aspect are you considering? What is important for you whenever you go and buy groceries? What do you want to eat? But sometimes it's quite challenging to make those questions to the AI solutions because they are considered being this stiff, opaque, black box. Input in, something magical happens, and then output, recommendation or prediction. So we set out to uncover and explore if these problems can actually be solved in some way. Because if not, there are already some complications where the operators either ignore the predictions, ignore the recommendations, either by, manually solving some of the anomalies themselves, or in some cases, maybe worst cases, wherever they see an undesired prediction, they turn it off. And then, you see, value lost. Lots of development time, lots of investment in the integration. It falls on the explanative aspect and it just doesn't work, or perhaps they forget to turn it on again. And as previously mentioned, yes, regulations. There is the EU Act that I think most of you have heard of that also puts additional requirements that the AI solutions should be more possible to audit, but also made more transparent. And this, in essence, allows us people to have control, to have the power, instead of the machines having control and power over us. We started a project called Explainable AI, standing for Explanatory Interactive Artificial Intelligence in the Industry, which had the objective to break down the major challenges of the so-called black box models in the process industries. 3 key goals. The first one regarding explainability or explainer components for increased understanding in the model output for end users. Additionally, if you have an output, you might think of it either looks good or perhaps does not look good, whether you accept it or perhaps you reject it. But then what do you do about it? There should be some possibility to affect it. So therefore also the possibility to provide feedback to some mechanisms to manipulate back that hopefully the models that are incorrect or need some type of improvements can actually be done that in some way. And then lastly, creating ML ops, a machine learning operational pipeline, reusing the already established mechanisms for machine learning, taking the agile learnings from development operations and also from data engineering, and integrating the explainability and also the interactivity components so they can become more naturally present in the development process. The circle that you see here is, well, more or less the traditional machine learning lifecycle, beginning from gathering data to structuring it, selecting which algorithm to choose, thereafter validating the model, and then eventually taking it to the industrial applications. So deploying, validating, testing, and then it's the usage. And in this, you will see examples, the usage use case, which will be the flotation use case. The Explain AI project was an international project consisting of partners from 3 different countries in 3 different consortiums: Germany, Sweden, and the Netherlands. And we actually looked at 8 different use cases, ranging from flotation process, provided by Boliden. Also, we had LEAG in Germany, looking at the price predictions of energy price predictions. In ProDive, Netherlands, they wanted us to explore how we can assume or explain whether the electrical circuit board predictions are false or false positive, and which are the aspects behind that. And then some additional ones regarding vibration monitoring in the pulp and paper industry, and some more. The duration was about 3 years. And also, as you see, partners ranging from academic research, technology providers, and of course, use case providers. And in this case, for Sweden, it was Boliden that wanted us to closer investigate and explore the flotation process that I think all of you know has to do about enriching and extracting the mineral concentrations from the ore pulp or the slurry by controlling the temperature, for example, adding additional air, adding the reagents, and then some minerals float up in bubbles, which for me is an amazing process that you actually have bubbles that extract precious minerals, and some of them actually sink down to the bottom. The challenges is that we wanted to better understand the accuracy in the concentration for copper, but also the accuracy and the frequency, so doing it at a higher rate. And then the other aspect is that obviously there are operators that have different experiences. Some of them working them for 3 years, some of them working at the place for 23 years. And there are differences in the type of control strategies that they apply. And perhaps by creating additional understanding through the models, through the AI, they will also get some additional learnings on how to control the process. So that is also something that hopefully would be a benefit by creating more transparency in some of the AI solutions that are present or will be present in the control of this copper recovery. So before we started, we applied the user-centered design process for XAI, standing for explainable AI. And then we started asking ourselves, scanning the prior art search and saying, what type of mechanisms or solutions exist today? We quickly found out that most of the explanation techniques, they are present for the data scientist. So what type of features that locally contribute to the prediction, which type of mechanisms that perhaps counterfactor that. And we started to ask, well, could it be that perhaps the operators would like to understand about the prediction, or is it the accuracy that they might be interested in? Should there be a possibility for them to provide some input to the model, or maybe if the model or the recommendation is incorrect, either partly or fully disable it? So it was a rather unexplored area. And which better way to do it than not to apply the user-centered design process that in a simple essence, consists of these three key steps. The first one is, of course, understanding their context and seeing things from their perspectives. By applying, for example, methods as, well, interviewing them, observing them, going out to the field, see who they communicate with, what type of activities they do, and that allows us to gather the information that, of course, afterwards we have to analyze to be able to find patterns across the different people that we have talked to. And that way becomes an establishment, a user research establishment that creates requirements for the technology development. Once you have that, you go back to the drawing board and, of course, use the insights that you have generated. So sketching, coming up with ideas, doing, well, either high-fidelity mock-ups that you can quickly test or iterate, maybe initially within your own team, but of course eventually towards the real users, which goes to the, well, third phase, which is the evaluation phase. So here going back and showing the solutions for the actual people and see how they react, and defining some measurable KPIs that allow you to measure if whatever you want to achieve through the new design actually is achieved or perhaps not. So here, yes, there are methods that are not, well, equally hard-coded when it comes to sometimes maybe the amount of bugs that might exist in a particular code. But here we have a possibility to measure how fast potentially they complete a certain task, how many of the recommendations that actually accept or they believe in, or maybe applying some of these subjective measurements, whether they like the solution or not, if you divide it into different classifications or features. And then from those learnings, you can iterate, go back to phase 1 or for phase 2, and repeat the process. Then there are different types of needs. The first one, when doing the user-centered design work, is that whenever you talk to people, they usually have a good way of expressing or saying what they do. And that's quite straightforward. But then there are some outspoken needs, because we sometimes forget, we don't remember everything, or we think we do certain things in the way that we think we do it, but that's sometimes not sometimes the case. And the last one is that sometimes people have a hard time of actually expressing what they really want, either how they do it or what type of goals that they might have. And to give you an example or two, if I would ask you what type of groceries you bought last week or last day, maybe you remember some of them, even though you do it, well, either, if not maybe every day, every second day. But then by looking at the receipt, perhaps you would see that there are some missing or some additional ones. So those are the unobserved or unspoken needs, because it's difficult to relate to it, even we do it very frequently. And the last one would be, yes, I actually had a dish, so I cooked this. But if someone would offer something else, perhaps that would be even better. So then the most recent latent needs. So during the course of the 3-year project, we divided our work and applied the user-centered design to first gather the requirements, then iterated some of the solutions, and eventually validated them a couple of times. And here is what we learned by a couple of interviews and through the research work, is that the operators expressed that they wanted to understand what type of variables or what type of features that actually contribute to the model prediction. How will the prediction change if I potentially change something else during the meantime? Or how accurate is the model prediction? Has it been in the past? Because quite often we saw that they look at historical situations to be able to understand what comes in the future. Also something else, if they saw that perhaps the model would be off, so either with a high uncertainty or a great bad accuracy, they wanted to see, is there something that I can do? Which parameters should I control to be able to, well, avoid it? So what are the countermeasures? And here, when being in the field, we try to, of course, create a mood where it's relaxing and open for them so they don't feel nervous, because you can imagine we coming there and asking them questions, and they might be thinking that what's the right answer. But there is no right answer. The right answer is whatever they say, whatever they do. It's us giving information about something that they experience in their profession. From those, user research insights, we created following solutions that had to do regarding explainability and explainer methods. So I will go through them in detail soon, but this is an overview. The first one is reference-based explanations, allowing them to look back in history. Second one focuses on how to actually introduce which signals or which features that matter for the prediction. Then there is some uncertainty information, because as I said, it's great, the predictions are good, but not always perfect. And also giving them the possibility to experiment by creating their own models, and then whenever the models are created, they can also compare which of those models that is actually the best. The first feature helped them to understand if this instance or prediction has actually happened in the past. And I will use the pointer here to better explain the user interface. So this line here, this states now. And here is the prediction. And with an uncertainty band. And what this graph shows is that this black line is a historical event that allows them to see the prediction was something like this, the uncertainty band, but it actually went outside, so the accuracy was, in this case, not that good. And also there is a possibility to add variables, so you can say, I would like maybe the CAX or the oil or some other reagents to be included, so they can compare which other variables that actually contribute or how they behaved, of course, across time. And this allowed the operators to, see how the prediction was in the past, but also compare it to some other, include some other variables. The comments that you see we receive that it's helpful, always helpful to see the past, because that might help them to understand which actions to take in the future. But some of them thought that the similarity criteria, how that was assessed, was not clear enough. And also the multidimensional similarity, that was also not easily not easily understood. And the ranging connected to the criteria was also not so very simple to understand. The next feature, which has to do with feature inclusion and sensor plotting, it reveals by indicating what type of variables that mostly contribute to the prediction. So, of course, in the flotation process, the couple recovery is very important to understand. And here, in the simplified process graphics here, not to reveal too much details, we created indicators. In this way, with these subtle blue dots, yet again, not to overpopulate with some of the information of which features mostly contribute to the prediction. This was a bit, mixed feelings from the operators. Some of them appreciated it a lot. We elaborated that whether it should be presented in a list or in relation to the process graphics, and many of them favor the process graphics because that is something that they are very familiar with. That's something that they look at every day. But some of them said that the features that they see the model is favoring is not the way they see, according to their understanding, how the process is behaving. And for us, I think this was both good and a bit of a surprise, because it allowed them to challenge themselves or challenge the model on whether they could educate themselves or perhaps the model needs to be improved. Then the uncertainty band. So the uncertainty band is this one, which says that the prediction will be within this area. And you see, the further in time you go, the higher uncertainty. So most of the users, they predicted or they appreciated it and understood that the uncertainty, of course, will increase over time, but some of them actually didn't realize what it meant, like why is it wider? But the ones that understood it said that it's good to see that the further ahead in time, and if the uncertainty would be even greater, then they need to be more present, more focused, because they get an indication that the model thinks something will be off. And most likely that is an indication for them that something might, well, be unstabilized. Then, possibility for them to explore a bit more. Here, we created a feature that allowed them to select, according to their understanding, which parameters and which variables should be favored by the model. Because obviously, if you have experience of 3 years or 23 years, and then again in relation to the model, they differ. So now we gave them a possibility to select, through this HMI, a certain amount of signals and say, create me a new model, train and favor this type of parameters. And then after the creation, it gives them the ability to yet again, of course, simulate it and see in a list represented here which type of models, according to some of the preferred variables, actually behaves the best. Either has the broadest uncertainty or perhaps the best accuracy. The operators, in this case that we talked to, they say that, well, selecting or deselecting and comparing these models is useful because it allows them to explore. But a few of them said, no, not for me. Give it to the data engineer, give it to the data scientist. I work with the process. This is not really my cup of tea. And some of them said, okay, it might be useful, but it's a little bit too far away for me to actually explore about the model performance. So by having these fast iterations and possibility to learn from the real users, we saw that it became faster and more apparent for us which features that I appreciate and help us to understand what to develop or what to not start develop, because of course every development process is costly and takes even more time. Also, it allows us to integrate some of the already mentioned more complex or emerging technologies by making sure that whatever comes in the workflow is more related to the already established workflow, because not everything changes at once. And here we got a rather quick signal from the operators is that they would like to have it closer to something that they already have, which is the process graphics. And also gave us the possibility for us to interpret what they want, what type of goals that they want to achieve, and allowing with this quick experimentation or innovation cycles. So creating these unmet needs, so it doesn't just become a, well, close optimization, but more of an innovation paths. The AI project, Explain AI project, also created this public guidebook that gathers the information of, well, the insights and the key findings that you're supposed to consider whenever creating explainability mechanisms. In this case, I'm mentioning the flotation process, but for all of the other use cases that we touched upon in the Explain AI project. It gathers the different roles that we included, of course, from the different domains, and also describes the tasks that we believe how we documented it, that should give you some understanding, additional understanding of what they do. But primarily, I would say it created this framework where you start with the user-centered approach and have the key problems and challenges that they might face, whether it is taking decisions during critical time situations, and then connecting it to which type of AI capabilities that might be useful to apply. So in this case, it was the prediction. In some other cases, maybe it's something else. Perhaps it's solution recommendations, or perhaps it's the analytical of the condition. And then after, which type of explainability needs that are present, and then how to actually do it. So either which visualizations to use, which interactive solutions to have, and of course, how to build the underlying technical infrastructure. So we were fortunate enough to have the possibility to connect the different pieces into a solution, into a pilot that was eventually tested in the Garpenberg at their flotation setup. And this, well, strengthened and increased the technical maturity level. And luckily for us, it awarded us a prestigious prize that ITEA thought that the solutions were so new for the areas that we research, and that they awarded us the Excellence of Innovation Award, that of course we happily shared with the rest of the world. But I'm very grateful for this close collaboration and fantastic support from Rasmus, helping us to gain access to the data, allowing us to coordinate with the operators on when to visit them, how to conduct the work, and then together creating additional holes, peeling off some layers from these black boxes. So it becomes easier to understand how it works, and you can see what type of features or signals that it actually considers. And of course, in this case, for the flotation process. So I'm grateful for that, and I very much look forward to some future collaborations. Thank you.